गुरुर्ब्रह्मा गुरुर्विष्णु गुरुर्देवो महेश्वरा गुरुसाक्षात् परब्रह्म तस्मै श्री गुरवे नमः.
Good morning, students. Today we are discussing binary number system. In the previous class, we studied about decimal number system. Let me recall your memory. The decimal number system is the system of the user. The user use decimal number system to represent all types of values. Decimal number system is a positional number system, but this number system is not used in computer. The computer uses a different number system. Those number systems are binary number system, octal number system, hexadecimal number system. The decimal number system has 10 unique symbols. Its base value is 10. We have seen the structure of decimal number system. Today, we shall discuss about the binary number system. The binary number system is a two-symbol system used in computer to represent all types of values. The binary number system uses only two digits. The two digits are 0 and 1. The 0 and 1 in computer represent presence of no signal and presence of a signal. 0 represents no signal, 1 represents signal. Your digital computer can differentiate between these two states. Those two states are represented by these digits 0 and 1. Only two symbols are used. Therefore, it is called binary. Bi means two. Since there are only two symbols used in binary number system, its base of number system or radix is 2. You can see the example given in this board. 10101 represent a binary number system. How can I say that it is a binary number system? It can also be a decimal number system value, because in decimal number system this value can be read as 10,101. Therefore, in binary, suppose the digit represented in binary number system, the value is represented in binary number system, then the base of the number system should be mentioned. So the base of the number system is written at the bottom, at the subscript position of the last digit. So in this example, the value of the binary number is 10101. The second example is different value, that is 1011.01. It is also a binary number system. The top example, that value represent the whole number. The bottom example value represent the fractional number. There are two parts here, the integral part and the fractional part. We can represent both whole number and real number using binary number system. The binary number system is a positional number system. Then, how do we represent the positional value of binary number system? Now, in the sequence of this binary digit, 1, 0, 1, 0, 1, which is the binary number. Here, this one is at the leftmost position. The rightmost position, there also the value or the digit 1 is present. The leftmost digit is called MSB and the rightmost digit is called LSB. What is the meaning of MSB and LSB? In positional number system, every value gets its magnitude by their position. That is, the leftmost digit value will be higher than least significant digit or the bit, LSB, least significant bit. Most significant bit will have the higher value than the least significant bit. The leftmost bit in the binary number is MSB. The rightmost bit in the binary number is called LSB, means least significant bit. So it represents the value which is higher and the lower respectively. How is that? How it represents the higher value than the lower value? Let us know the positional value of the face value of the digit 10101. Let me write like this. What is the position of every digit given in the example? This is a binary number. Now, let me start from the rightmost digit, that is the least significant bit. The least significant bit located at the position of 2 to the power of 0. What is 2 here? The 2 is the radix of the binary number system. And 0 represents its positional value. Then the second digit left to the least significant bit is 0. Its position is 2 to the power of 1. Then the third digit, now we are incrementing. So we are moving from right to the left. Okay. So this becomes 2 to the power of 2 and this position is 2 to the power of 3 and this position is 2 to the power of 4. This is called positional value. And this is called the face value. In the last class I explained about the face value and the positional value. The face value remains the same irrespective of its position, but the value at the position will be multiplied to the face value and the sum of those resultant value will produce the final result. Let us see how is that. Now, what is 2 to the power of 0? If you solve, what is 2 to the power of 0? The 2 to the power of 0 is, what is 2 to the power of 0? 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3, yes, some may have the doubt, is it 8 or 6? Let me tell you how this should be calculated. 2 to the power of 3, nothing but 3 times 2. 3 times 2. What is 3 times 2? Let me give the working here. 3 times 2. 2 into 2 into 2. 2 times 2 is 4. 4 times 2 is 8. Don't multiply 2 into 3. It is not correct. It should be 3 times 2, which is the base of the binary number system. Here you make the mistake. I am repeatedly telling this. How 2 to the power of 3 should be calculated. That is 3 times 2, 2 into 2, 4, 4 into 2, 8. That is the value, the final value of 2 to the power of 3. What is the value of 2 to the power of 4? That is, 2 to the power of 4 is nothing but 4 times 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. Okay, so this is 16. Okay, so we solved the value, the positional value which is given in the form of 2 to the power of 2, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1 and 2 to the power of 0. Now this is the resultant value of the base raised to its position. Base of the number system raised to its position. Right? Now this value should be multiplied by the face value. You have to multiply this value. Okay? Multiply to which value? Positional value should be multiplied with the face value. So that gives the number, see, 16 into 1. 16 into 1. Then 8 into 0. Then 4 into 1. 2 into 0. And 1 into 1. After multiplying this, what we should do? We should add these numbers to get the final number. Plus, 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 and plus. So, what is 16 times 1? 16 plus 8 times 0 is 0, 4 times 1, 4, 2 times 0, 0, plus 1 times 1 is 1. Now you add all these numbers. 16 plus 0, 16, plus 4, 20, 20 plus 0, 20, 20 plus 1, 21. This 21 is a decimal number that is represented in the binary number system as 10101. I hope you have understood. Then let me take the second example, 1011.01. What is the binary 1011.01 in decimal number? How it should be calculated? Now, the number is 1010 dot, say 101 is the value. Now, you have to take the integral part separately, fractional part separately to decide the final value. Here in the integral part, this one at the leftmost position is MSB, and in the integral part, the 0 is present at the rightmost place called LSB, and in the fractional part, the 1 is at the leftmost position, MSB, and 1 is located at the fractional part, is identified as LSB, least significant binary digit or bit. Okay. Now you write the positional value of these digits. That is 1 0 1 0 dot 1 0 1. Positional value of 0 is, I can write at the bottom 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power of 2, and this is 2 to the power of 3. Dot, what is the positional value of 1 at the fractional part? 2 to the power of minus 1. This is 2 to the power of minus 1. There is no 2 to the power of minus 0. So, the fractional part begins with 2 raised to the power of minus 1. The second one, 2 to the power of minus 2, and this is 2 to the power of minus 3. Now you know that what is the positional value in the decimal. What is 2 to the power of 0? 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. This you know now. Remember the pattern. 1, 2, 4, 8, 16, 32, 64. Like that it goes on. Multiples of 2. Now, some of you find difficulty in calculating 2 to the power of minus 1. How do we calculate 2 to the power of minus 1? See, the 2 to the power of minus 1 means, 2 to the power of minus 1 means 1 divided by 2. What is 1 divided by 2? 1 divided by 2 is 0.5. Then what is 2 to the power of minus 2? 2 to the power of minus 2 means, what is 2 to the power of 2? 2 to the power of 2 is 4. So, we have to write 1 divided by 4. What is 1 divided by 4? That is 0.25. Then, what is 2 to the power of minus 3? How do we calculate? How do we know that it is, what is the value of 2 to the power of minus 3? So, 2 to the power of minus 3 is nothing but 1 divided by 2 to the power of 3. What is 1 divided by 2 to the power of 3? 2 to the power of 3 is 8. That is nothing but 1 divided by 8. So, the answer is 0.125. So, the positional value can be written in the form of a decimal number. That is, 2 to the power of minus 1 is 0.5. Then 2 to the power of minus 2 is 0.25. And 2 to the power of minus 3 is 0.125. So, you have to multiply this value. Multiply this value with the respective positional value, place value of the digit. So that is 1 is multiplied by 8. 1 times 8 is 8. 0 times 4 is 0. 1 times 2 is 2. 0 times 1 is, what is 0 times 1? 0. Then 1 times 0.5 is 0.5 plus 0 times 0.25 is 0. Any number multiplied by 0 is always 0. 1 times 0.125 is 0.125. What is the net value of this? 8 plus 2, 10. So, the individual part is 10 point. What is 0.5 and 0.125? So, that comes to 0.625. So, this 0.5 is nothing but, you can write like this, make it the length equal to this digit, then you will understand. 0.5 is 0.500 plus 0.125. That is 0.625. So the final answer is calculated. This 1010.101 is actually representing 10.625 of the decimal number. This is how in computer the entered decimal number will be represented using the binary number system. Now, in decimal number system, we count. How do we count the decimal number? Everyone is familiar. How it is counted? We start from 0. This is counting of binary number. To explain counting of binary number, first I am taking the decimal number. So 0, 1, 2, 3, 4 and so on. In binary, how the 0 is counted? I am giving in binary, the counting of binary is given here. 0 in, this is all decimal number. Okay. How do we count in binary number? 0 is the first value in binary. Also, 1 is the second value in the binary. But we don't have the symbol 2 in binary number system. Now, let me ask you a question. After 9, that is 1, 2, 3, 4, 5, 6, 7, 8, 9. The next value, how do we write in decimal number system? The least value is 0 and the next value is 1. The 1 will be written at the left side. That will be written at the left side. Then the next number is 1 and 1. 1 and 2, 1 and 3. Like this we write. Okay. See, 1 in the leftmost position, 0, 1, 2, 3, 4, 5, 6, up to 9 we write. Then we select the next digit towards the right. Then we write 20, that is 20, that makes 20. The same mechanism is used in counting binary number also. This is very, very important to understand how the binary numbers are counted. Now, let me use the same principle here. 0 and 1. 0 is the first number, 1 is the next number. So, the 0 is written in the rightmost place, the 1 is written at the leftmost place. This is the third number. Okay. What is the next number of this? So, now 0 and 1 is taken. So, 0 and 1. The next value is 1 and 1. The 1 and 1 is the value 3. 2 in binary is 1, 0. Now we are counting 0, 1, 1, 0, 1, 1. After this what, sir? After this what? See, this is 2, this is 3, 0, 1, 1, 0 and 1, 1. Now the least value is 0. The next value is 1. Higher values of the decimal numbers cannot be represented using binary number system alone. It is because the higher decimal value requires more number of sequence of binary digits. Therefore, the octal number systems and hexadecimal number systems are used to represent higher value of the binary digits. Let us see the octal number system. Remember, octal number system is also used in computer to represent larger quantities. The octal number system, the use of octal number system reduces more number of binary digits to represent higher value. So, the octal number system uses 8 distinct symbols. There are 8 symbols used. What are those 8 symbols? The 8 symbols are 0, 1, 2, 3, 4, 5, 6 and 7. Up to 7, 0 to 7. There is no 8, 9, 10 or say 9. It uses 8 binary, 8 octal digits. Those digits are given here. 0, 1, 2, 3, 4, 5, 6 and 7. Stop. That's all. Okay. So, since there are 8 distinct symbols used in the octal number system, its base value or a radix is 8. That is, every octal number represented, okay, using a subscript of 8. As given the example, I have given an octal number 375. This can be a decimal number also. Then how do we indicate that this is an octal number? We attach the radix of the octal number system, that is 8. So this becomes 375 base 8. It should not be pronounced as 375. It should be taken individually. 375 base value is 8, represents the octal number. Now, what are the positional value in the octal number? In this 375, which one is the most significant bit? The 3 is the most significant bit and 5 is the least significant bit. The same principle goes because octal number system is also a positional number system. Here I have given the positional value in the form of octal number system. So, the positional value in the integral part begins from a to the power of 0, a to the power of 1, a to the power of 2, a to the power of 3, a to the power of 4, a to the power of 5 and so on. It can be any length. At the fractional part, again, the base of the number system is 8, a to the power of minus 1, a to the power of minus 2, a to the power of minus 3 and a to the power of minus 4 and so on. Same as binary number system and decimal number system, because all these number systems belongs to positional number system. Only the base value changes, otherwise the structure of representing their positional value remains the same. Since it is an octal number, their position mandated by the radix of that number system, that is 8. In binary number, the same structure is used. This 8 is replaced with binary 2 because the radix of the binary number system is 2. If it is a decimal number system, the radix of the decimal number system is 10. You remember, all these positional value in the decimal number system is written as 10 to the power of 1, 10 to the power of 2, like that. So let us see the similarity and understand the structure of the positional number system. It remains the same. So, what is a to the power of 0? Any number raised to the power of 0 is 1, I said in the first class itself. So, a to the power of 0 is 1, a to the power of 1 is 8, a to the power of 2 is 64, a to the power of 3 is 512, a to the power of 4 is 4096, a to the power of 5 is 32,768. This is the integral part. What about the fractional part? The fractional part, here 3 places are given. A to the power of minus 1. How do we write a to the power of minus 1? How do we calculate the value of a to the power of minus 1? To calculate a to the power of minus 1, we have to write a to the power of 1. What is a to the power of 1? 1 divided by 8. What is 1 divided by 8? 1 divided by 8 is 0.125. Okay, now calculation is very easy for you because you can understand how these a to the power of negative value, raised to negative value, how it is being calculated can be seen here. So, what is a to the power of minus 2? So, 1 divided by a to the power of 2. What is a to the power of 2? You can see a to the power of 2 is 64. There it goes, 1 divided by 64. What is 1 divided by 64? If you use your calculator, you will get the answer. That is 0.15625. That is what written here. And a to the power of minus 3 is nothing but 1 divided by a to the power of 3. 1 divided by a to the power of 3 is, that is 1 divided by 512. 1 divided by 512 is 0.001953. Now let us calculate what is 375. What is the value of 375, octal 375 in decimal number. So, let me write, there is no fractional part in this value. Let me write 375 in the respective places. So, it is a to the power of 0, place is 5, a to the power of 1 place is 7, a to the power of 2 place is 3. 375. Now you know how we calculate the final value. How is it calculated? 375. This is a to the power of 0, a to the power of 1, a to the power of 2. What is a to the power of 2? A to the power of 2 is 64. 7, a to the power of 1 is 8. A to the power of 0 is 1. 3 times 64. 7 times 8. 5 times 1. If you calculate and find the sum of it, will give you the final value. So, this is 192. This is 56 and this is 5. So add all the three values, 192 plus 56 plus 5, that comes to 253. 253 is a decimal equivalent of the octal number 375. I hope you have understood the octal number system. So, octal number system uses 8 distinct symbols. They are 0, 1, 2, 3, 4, 5, 6 and 7. The base value is 8 and the structure of octal number system as given here, it is same as the binary and the decimal number system. Next, the next number system is the hexadecimal number system. Even sometime octal number system will occupy more binary digits to represent the higher value. Therefore, to represent higher value in computer, hexadecimal number system is used. It uses very less digits than binary and the octal number system. So very larger values are represented using hexadecimal number system in computer. The hexadecimal number system uses 16 distinct symbols to represent the value. It is a 16 symbol number system. Hexa means 6, decimal is 10. Therefore, it is a combination of decimal and the alphabet symbol system, because we carry all the symbols that are used in the decimal number system. As you can see on the board, the symbols that are used in the hexadecimal number system is the decimal 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, to represent the value 10, 11, 12, 13, 14 and 15, the alphabets, English alphabets are used. The 6 symbols are represented using alphabets A, B, C, D, E and F. They represent the decimal equivalent, decimal value 10, that is A, 11 is B, 12 is C, 13 is D, 14 is E and 15 is represented using alphabet F. There are totally 16 symbols. Hexa means 6, decimal means 10. There only you can understand what is the base of hexadecimal number system. It is 16. The radix or base of the hexadecimal number system is 16. The example for hexadecimal number is, say, 2D8. What is this 2D8? What is the D here? Now you have to identify the decimal equivalent of D. If you identify the decimal equivalent of D, that is, this is 10, 11, 12 and this is 13. So this is 2, 13 and 8 in the hexadecimal. See, some hexadecimal will be represented using purely alphabets. The second example, that is, say, DAD, dad. So what is D value? The D value is, as you can see, 10, 11, 12, 13. 13. D value 13. A value is what? Is 10. D value is 13. So the value 13, value 10 and value 13 in hexadecimal is represented using the alphabets, because those are the letters used to represent these numbers. So the 16 is given at the subscript position because this number represents the hexadecimal number. Okay, so we will continue in the next class, and you have to solve the questions that will be given on the slide. Please note down and solve the questions.